All right, so today is going to be a review of power series, the tool that we're going to be using to this is the tool that we're going to be using to deal with linear equations when the coefficients are not constant. So when they're functions in terms of the fix the light levels a little bit. Okay. So well, you've seen power series before in Calc 2, but I'm going to well, there's no harm in looking at this with a fresh set of eyes. So I'm going to kind of start from first principles. Let's look at the polynomials. Polynomials are something that we've been dealing with a lot. And so if we take two polynomials and we multiply them together, let's say 1 minus x and 1 plus x, we get 1 minus x squared. Every time we multiply polynomials together, we get something that has the degree is the sum of the degrees of the two things. So if we, for example, instead did 1 plus x squared, what do we get? We get 1 minus x cubed. We get something, this is degree 1, this is degree 2, so on. Now, let's say we extend our idea of polynomials. Polynomials are powers of x, some linear combination of powers of x, right? But only a finite number of them. So what we'll do is we'll extend our idea from polynomials to things where we can have an infinite number of powers of x in our linear combination. So let's say I just continue. I can, of course, only write a finite number of them. So I'll write an ellipsis to indicate that there's going to be, it's going to continue on like this forever. So it's going to be x to the fifth and then x to the sixth. This is going to continue on forever. There's going to be a never-ending supply of these powers of x. And I'm going to do what feels like the obvious thing, which is to say that if I want to multiply these things out, the rules of algebra work exactly the same. I'm going to take this 1, and when I distribute that 1 through, that'll give me all of those terms. So I'll get 1 plus x. I was thinking x squared, so I wrote it. X squared plus x cubed plus and so on. And then when we multiply minus x through, we're going to get minus x squared minus x cubed minus so on. And if the rules of algebra work exactly like we think they should, then we'll get cancellations for all of these things. And what we end up with at the end is 1. So when we extended our idea of polynomials from something that only has a finite number of powers of x to something that can have an infinite number of powers, what we see is that when we multiply these things together, we can actually get a lower degree. Now, all that we've done with this infinitely long polynomial-like thing is we've declared that we can do algebra with it. But we've said the rules of algebra work exactly the same here as they do everywhere else. We're just going to say that's a rule. And when we do that, what we've created, these are called, this is an example of a formal power series. Now, doing algebra like that is something that we could have done with polynomials just the same. But polynomials also have another property. We can plug something in for x and get their value, right? If we had 1 plus x squared, and we plugged in 1 for the x, we would get 1 plus 1 plus 1, which is 3. And if we had 1 plus x squared plus x cubed, we would have gotten 4, and so on. However, things like that become a lot more complicated when we. So, in order to make this into what we really refer to as a power series, formal here means that we're only treating it as a string of characters, letters and numbers, plus signs, things like that. And we allow ourselves to do the rules of algebra, but we don't necessarily give it a meaning whenever we plug in an x. So in order to give it a meaning, we have to make sure that we can come up with some meaning. And the meaning, well, you've already seen this how too, but the meaning that we give to it is we look at the partial sums. So we look at 1, and then 1 plus x, and then 1 plus x squared. Just for the sake of illustration, 1 plus x squared plus x cubed, and so on. For any particular x, this gives us a sequence of numbers. And if the sequence with this of partial sums, so we call these things, just a name, we know what they mean. If these get arbitrarily close to something, in other words, they have a limit, then that something partially close to something, arbitrarily close to something for a particular x. Let's say x is equal to x0. Now let's say x is equal to, let's call it c, some constant. Then that something is said to be value of 1 plus x squared plus, and so on. In other words, the formal power series. So once we have that bit of information, then we will call this thing a power series. So if it's a power series, then we can plug in some value for x and get some output, but we need to know what values of x work. So that's the question. Now we saw in Calc 2 how to work with this. Let's suppose that x is greater than or equal to 1. Then what we get is 1 plus x. Well, let's just say, how should I say this? What we're doing is if x is greater than or equal to 1, then 1 plus x squared, so on. Each time we're adding something positive and bigger. Or if it's just equal to 1, we're adding 1 over and over and over, right? Now these partial sums, we know these things will never settle down to something. They'll just keep getting bigger and bigger as we go on. And so in this case, we say that this limit doesn't exist. And so the term that we give that is diverges. Or it diverges whenever x is greater than or equal to 1. Now, if x is less than -1, then what do we have? We have 1, and then we subtract something, and then we add something even bigger, and then we subtract something even bigger. I've given up on writing in mathematical notation. This is an illustration. We're doing this kind of roughly because you've seen the proofs before. But it's kind of obvious that it's just going to keep bouncing back and forth between bigger and bigger positive and negative values. And so it's never going to settle down to this divergence as well. Whenever we have x between -1 and 1, not inclusive, well, we had another proof for this that I'm going to skip for now. But we know that it converges in this range. But let's look at what happens when it's equal to 1 and -1. So if x is equal to 1, we get 1 plus 1 plus 1 plus, and so on. So we say this very clearly diverges. Our sequence of partial sums would be 1, 2, 3, 4, and those don't settle down to anything. They just keep going forever. X minus 1 is a little bit different. We get 1 minus 1 plus 1 minus 1 plus 1 minus so on. And the sequence of partial sums here are 1, 0, 1, 0, 1, so on. So this doesn't settle down to anything. However, it doesn't blow up to infinity, and it doesn't blow up to negative infinity, and it doesn't sort of, keep getting bigger like this thing does, going in opposite directions, and it doesn't keep getting bigger like this thing does, but going towards positive infinity. It just kind of oscillates back and forth. So we also say that this thing diverges because we have a very strict definition of what it means to converge. And that is only if the sequence of partial sums settles down to zero. So it's the only time we're going to give this thing meaning. We'll see in just a moment that maybe that's a little too strict, but it's what we're going to stick with. Okay. Now, what we saw was that we take 1 minus x, and we multiply it by this thing. And so on. By the formal power series, we get that this is equal to 1. So if we assign a value to this thing where it converges, then we know what it must converge to, because that multiplication has to continue to make sense. So what it has to converge to is 1 over 1 minus x. It has to converge to 1. So we've looked at where it converges and where it diverges, and we've also assigned a value to this thing. We had a name for this. This was the, we called it the geometric series before when we considered x to be some constant between -1 and 1. So now we'll call it the geometric power series. And if we say f of x is equal to 1 plus x squared plus x cubed and so on, if we now treat this like a function where we can plug something in for x and get a value out, we have to be clear on what we mean by this function. Ordinarily, when we deal with things that are in terms of a formula, that formula is something like a polynomial or an exponential or a trig function or something like that. And in all those cases, no matter what we plug in, it's totally fine. But in this case, there are values that we can't plug in. Oh, maybe sometimes, we can't plug in something that makes the denominator 0, things like that. So we have to say not only what this thing is equal to, but where it's defined. And so we'll say that f, remember this function signature notation. It's a function from the interval from -1 to 1, the reals. And this is where we specify that restriction. We give this thing meaning, but only right here, only for these particular exponents. Okay. So this geometric power series it's a good first example of a power series. It's very simple to write and to remember. We know exactly what it's equal to when it converges. And it's also useful because we can compare other power series to it. Now, of course, we can take this thing and we can shift it left or right on the real line, just like we could any other function. And so if we wanted to take this, whatever this thing was equal to, and we wanted to shift everything forward on the real line, we wanted to graph this thing, what it looks like. We could shift this thing forward by just replacing x. Let's shift it forward 1. We replace x with x minus 1. And we would do that like this. So this is f of x minus 1 is equal to this. And this is some new function where it's just the old function. We've shifted it forward by 1. And this thing will now be defined from not from -1 to 1, but from 0 to 2. We can take this thing and we can shift it to the left, right, just like we would any other function. Okay. Now, if we look at this geometric power series, we see something special happens when x is equal to 0. When x is equal to 0, we get 1 plus and then a bunch of zeros. And this always happens for power series. There's always a value that we can plug in that will give us only that first term, and then all the rest of the terms will be equal to 0. So here it's 1. Here, if we plug in x, or sorry, it's 0. If we plug in 1 here, we get this is 0, this is 0, this is 0, and so on. So that's going to be called, this is the center of the power series, like the center of a circle. And well, you probably already remember this, but that has this analogy with the circle goes a little bit further. But anyway, any power series will have a center, and that center will give us whatever this constant term here is. So at this point, I think we'll go ahead and define in general what a power series is. I will write it. So it will be, we can always write it like so. So there will be some coefficients. So there'll first be a constant coefficient. And then in general, we can have this will be centered at x0, we'll say. And then we have the quadratic term and the cubic term, so on. So this is anything that we can write in this form, we will consider to be a power series. Now, if we go forward in the coefficients and eventually the rest of them, they're all 0, then we only have a finite number of powers of x or powers of x minus whatever our center is. And we just get a polynomial. So polynomials are included in this idea. And of course, polynomials will recover the exact same definition of the meaning of a polynomial or the value of a polynomial at a particular x, because eventually the partial sums will just be constant. They'll eventually be the same thing forever because so this is really a perfect extension of polynomials. Now, one way we write this is in summation notation. We'll find this to be useful as we go on, because we will be taking different power series and comparing their coefficients in order to do this thing that's sort of like the method of undetermined coefficients, so that we can find solutions. So this will sometimes be useful. We just mean that we have an index that goes from 0 to infinity, and we've called it n. And so our coefficients are an, and that'd be multiplied by x minus the central power of n. And what it means for it to converge is if the limit as m goes to infinity, the sum from n equals 0 up to m of our power series. So partial sums, again, if we do the partial sums, we're just dealing with polynomials. So these things always exist. Their limit as we go through them may not exist, though, or it may not, the limit may not exist, it may not. So if this exists, then, and remember what I said about existence, we can sometimes say that the limit is equal to infinity or negative infinity. Those don't count as existence. That's just a shorthand for saying it diverges, but it diverges in a special way. So we say this exists, then the power series as that value, as the value of whatever the limit. So that's what we mean by convergence. Now, a very useful way of looking at these things is if we take our power series and we get the associated version of this power series where all of the terms are guaranteed to be positive. So we take the absolute value of each of the terms in, and because of the properties of absolute value, we can rewrite this thing. 0. Absolute value of an times absolute value of x minus 0 n. Now, if this version of the power series converges, the associated one with all positive terms converges, then the original power series, the one that came from, the one with possibly having negative terms, is said to converge absolutely. So it's said to converge absolutely, or it has absolute convergence. And this is an interesting property. Now, if we have absolute convergence, then we also have convergence, right? We know that although the original thing, which may have positives and negatives, may bounce around somewhere, it's going to bounce around and be bounded by what it would have been if they were all positive. So it's going to be stuck underneath that possible limit. And so it's guaranteed to converge. If it's absolutely convergent, it's guaranteed to converge. However, the other direction is not always the case. And you saw some examples of this in Calc 2, for example, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. This converges. It took a little work to show that it converges, but it does. Well, it didn't take really that much. However, 1 plus 1/2 plus 1/3 plus 1/4 diverges. So the associated series that has only positive terms diverges. This was called the harmonic series, and it's an important one to know about because it's sort of the archetypal example of a series that looks like it should converge but doesn't. So we had a proof of this, that it doesn't converge. However, this one does converge. And so instead of saying it converges absolutely, we can signify that it converges but doesn't converge absolutely by saying it converges conditionally, on the condition that we don't mess around with it. And well, first of all, maybe it's interesting to see what this converges to. It converges to the natural log of 2. If you hadn't seen that before, you might not have expected that. Kind of an interesting fact. But a strange situation comes up for conditionally convergent series. Whenever we do a polynomial, we do addition, and the order of the addition doesn't matter. For a power series, the order of the addition, it turns out, does matter. And what happens is that a conditionally convergent sequence, we can rearrange the terms so that it converges to any value. We can rearrange the terms so that it converges to anything. So already when we're dealing series, we're getting into things that seem like they kind of are strange. They violate our expectations. Doesn't mean it's a paradoxical, it just feels paradoxical. So we can rearrange them so they converge to any value or diverges. We can make it diverge as well by rearranging the terms. So that's why absolute convergence is an interesting property, because in that case, order doesn't matter. It's always going to converge to the same. An interesting property of absolute convergence. Now, a useful way of figuring out if things converge is, well, let's go back to our original example. So long as this thing converges, what it converges to is 1 over 1 minus x. And we had shown that before. So it converges only when -1 is plus x plus 1. And if we look at the value that comes out of this, that totally makes sense when x is equal to 1. However, when it's equal to -1, it seems kind of strange. So we'll have to come back to that. But here's the useful idea. If we look at these, then each term differs from the one before it by multiplying by x. Right? We have a constant ratio between the terms. That ratio is x. So that suggests to us an idea. If we take a power series and we look at the ratio of the terms, we look at them like this. We take a term and we divide it by the term before it. And then we take the absolute value and we say, how big is that? Because this thing converges when the absolute value of x is strictly less than 1. So we take this and we say, well, the ratio may not be constant, but if we take the limit as n goes to infinity, maybe that ratio goes towards something. It goes towards a constant. It gets closer and closer to some constant. So we'll do a little algebra to rearrange. we'll pull the x minus x0, the n plus 1, over x minus x0 to the n out. That's just absolute value of x0 times the limit as n goes to infinity of a n plus 1 over a n. Does this thing converge to something? So if it does, we'll call it L. Now, if we do eventually have a ratio, I'm noticing a little bit of lag. Oh, internet's not so good today. Does it look okay on your end? Okay, good. Maybe it's just mine. So now let's say this is our ratio for a particular x. You know, we get a particular x minus x0, and for our series, this is based on the L is based on the coefficients. We settle down on a particular ratio as we go forward. And this ratio is, let's say, bigger than 1. So let's say this thing is bigger than 1. Then if we go just a little bit lower than whatever we got as the ratio, then we can add a little correction term to just finitely many values. For all of the other values, we will have a ratio that is at least that big. So let's say we just look for something just a little bit lower, then we only need to add the correction term to a finite number of terms in order to get them all to have that ratio, right? And because it's only a finite number of corrections, that's just a finite value. That finite value is not going to change if it converges or diverges. And now we're looking at this thing that has a constant ratio, and that constant ratio is bigger than 1. And so that tells us, because of this, right, the absolute value of that ratio is bigger than 1. That tells us that this diverges. And not only it diverges. There's not a concept of absolute divergence. If it diverges, it diverges. If it's less than 1, then we can do the same thing, except we increase that value just by a little bit. We move it a little bit towards 1, and then we say we make some small correction to all of the terms, or maybe a large correction, but it's only a finite number of corrections. Maybe large finite values, maybe a large finite number, but a finite number of large finite numbers, even if they're big, they add up to finite. That's not going to change whether it converges. So then we compare it to this. We find that the ratio after being corrected is less than 1, and that gives us convergence. And not only convergence, but because we were doing this looking at the absolute values of the terms, we get absolute convergence. And if it's equal to 1, then like you saw in Calc 2, this is inconclusive. We'll just say, oh no. The ratio test, well, we call this, I'll give it a name, although you've seen it before, called the ratio test. For people who don't remember and are watching the video, hello from the past. We don't get a conclusion from this, and we have to test it using some other method. Okay. Now we see that the convergence or divergence depends only on our distance from the center. This part, this L, depends completely on the coefficients, and that doesn't change with the value of x. But this x minus x0 part does, and it varies with the distance from the center. So what we see is that as this x minus x0 gets larger, as our distance from the center gets bigger and bigger, eventually we hit a point where we go over this value is greater than. So we hit a point where it's equal to 1, and then beyond that, it's greater than 1. And so what we see is that Well, maybe I'll come back to the example. We got about 22 minutes. So that's how these things behave. This power series are nice in this way because they have this kind of very predictable behavior. There's the center where it converges, and then as you move away, it may diverge immediately, or it may converge for a little while and then it diverges, or it may converge everywhere. And we're only thinking of this for now. So we say that it has some kind of radius, x minus x0 less than rho. So it looks like a p, but it's actually the Greek letter rho for radius. And we say it converges absolutely in this range. So this is, we haven't gone too far from the center. And then x minus x0. Then we have gone too far and it diverges. This is called the radius of convergence. So that's how far we can get away from the center. It always converges at the center because we've got that A0 and then a bunch of zeros. But as we move out, things may act different. Okay, now this gives us some interval. So we go from x0 minus rho. So we go to the left by rho, and then we go to the right by rho. And this is called our interval of convergence. And this is just a way of putting the center and the radius together in a single notation. We're just stating whatever we already know, but just in different form. So there's nothing new added, different way of writing. Okay, now let's do an example. Okay, so this series that we're going to deal with is going to go from n equals 1 minus 1, n plus 1, n, x minus 2, n. This is x minus 2 minus 2 times x minus 2 plus 3 times x minus 2 minus 4 times x minus 2, squared, cubed, so on. So that's this power series. And we're assuming that the index 0 term is just 0. So we're not fitting that in. So we want to know where does this converge, or does it converge? Well, it definitely converges when x is equal to 2, converges to 0. So we know that it's centered at x equals 2. We know that much. But what about its radius of convergence? Well, we can use the ratio test. And I'll show all of the details now. And as I go forward with the passage of time, I will become more and more lazy. And I will not show steps that I think can do a lot of this. Anyway, the n plus 1 term will be, what do we get when we plug in n plus 1? Get n plus 2 here, n plus 1 here, and n plus 1 here. Hopefully my screen is keeping up with me pointing at things. Okay. Divided by the n term. So that's minus 1, the n, x minus 2 to the n. Now, n plus 1. So the n plus 1 cancels out with an n plus 1 here and just leaves just a 1. So it's just negative 1 left over. I get x minus 2 I just get a x minus 2 there. All of these cancel out with all but one of those. And I move the absolute value of it out. Absolute value. The limit as n goes to infinity of -1 times n plus 1 over n. And I could have done this in one step as well. This -1 is an absolute value, so that's going to go away. So what we get is the value of x minus 2. The limit as n goes to infinity of n plus 1 over n. And if you remember how to compute limits, you'll see that this limit right here is just equal to 1. So what we get is absolute value of x minus 2. And now we want to compare this thing to 1. So we want that to be less than 1. The L that we got here, this was our L. This was just 1. And so what we have is that it just depends completely on this this thing being smaller than 1. So in other words, the radius will be 1. Right? This thing will scale. This part scales the radius. Right? So the radius is 1, and it's centered at 2. But we can do a little bit of rewriting if we want to make it easier to look at. What we do is we say that if the absolute value of x minus 2 is less than 1, then x minus 2 is less than 1. And should I say this? Trying to think of a way to do this in one piece. So what we have is that the value of x minus 2 is somewhere between 1 and -1. If its absolute value is lower than 1, between 0 and 1, it has to be between -1 and 1. And now we can add 2 to both sides, and we get x is between 1 and 3. So from this point right here, we already knew that the radius was 1. We knew that the center was 2, and so we could have gone directly to that. But if we take this expression right here, we can do a little bit of algebraic manipulation and see that our interval of convergence is 1 to 3. So it's just a little bit of work. Okay, next. We want to determine the radius of convergence. The power series n equals 1. I don't know why in the examples this is the first time they introduce a power series where the indexing starts from 1. Maybe they're trying to throw you a curveball, and you'll notice that it really doesn't matter if it starts from 0 or 1 or -100 or whatever. We're only looking at the ratio of terms to figure out if it converges. So it really doesn't matter. Now, if we do the ratio test on this, what do we get? We get the limit. N goes to infinity of, let's say, the n plus 1 term. That will be x plus 1 to the n plus 1 over n plus 1 2 to the n plus 1 divided by, so I'll multiply by the reciprocal, n 2 to the n over x plus 1 to the n. Right? So we got a lot of cancellation. We're left with one copy of x plus 1, one copy of 2, and then n over n plus 1 is equal to I did skip a step in the previous problem. Well, we'll do it in this one. We'll continue in this one. Now, I really didn't, depending on what you're asking, what it's asking for, I really didn't. But what we'll get is absolute value of x plus 1 over 2 times the limit as n goes to infinity of n over n plus 1, which we see very quickly. This limit is just equal to 1. So this is the absolute value of x plus 1 over 2 less than 1. And in the very beginning, we could have seen that based on the way this thing is written, the powers are of x plus 1. So we get that the center is equal to -1. We already had the center before we even did any work. Now, when we look at this expression right here, we see that x plus 1 over 2, the absolute value of x plus 1 over 2, less than 1. That gives us where it converges. We just multiply both sides by 2, we get absolute value of x plus 1 is less than 2. And this, it's very easy to read off from this expression what the radius of convergence is, just 2. So how far can we go from -1? We can go a distance of 2. Now, the thing that I left out, we said this was the interval of convergence. Need to be a little more careful. This is where it converges absolutely, but on those endpoints, it might converge conditionally. So let's see what happens on the endpoint. We know it converges at this thing converges absolutely if we just do the same thing we did in the last problem. So we get exactly what we would expect for something that's centered at -1, and we can go 2 in either direction. It converges absolutely from here to here, but what about at the endpoints? Well, we can plug in the values and see what we get at those endpoints. So if we plug in -3 for x, we get the sum from n equals 1 to infinity. See, that's -2 to the n over n 2 to the n. And so this is the sum from n equals 1, or n equals 1 to infinity of -1 to the n over n. We just cancel out those 2 to the n. Well, this is the alternating harmonic series. And so this is just equal to, well, it's the negative of the alternating harmonic. Correctly. Anyway, this thing converges, but it converges conditional, which is no problem. Now, if we plug in 1, then in that case, we get 2 to the n over n 2 to the n. And so this is the harmonic series which diverges. So if we want to write the interval of convergence, we need to include the fact that it converges conditionally whenever -3, when x is -3. So the proper way to write this would be to include -3, but not include 1. And so that gives us our interval of convergence. Now we call it the interval of convergence because if we look on the real line, maybe zeros right here, rows right here, it converges from here to here. Have these values. Really, the I don't know if the right word is the appropriate way to look at this, if it's the better way to look at this, but it's certainly the more interesting way to look at this, which is that instead of looking at these things just on the real line, just looking at power series in the real line, we can look in the complex plane. And in the complex plane, all of this notation worked out exactly the same, and we get that the distance from the center determines where it converges. And so what we get in the complex planes is instead of a line segment where it converges, is actually a circle where it converges. right? So really this center and radius terminology actually works in a very interesting way. Okay. Now, see how much time I have. Okay, I got time. Okay, so let's do some more manipulation with these power series. So let's say f of x is equal to a n x minus x 0 n, and g of x is equal to b n x minus x 0 n. We're going to assume these are centered at the same point. Now, and we're going to say that they both have radius of convergence. They both converge whenever we're within rho of the center. So what happens when we add them together? Well, we can add them together termwise, or we can subtract them. F plus or minus, let's just say plus. Mentally substitute minus if you want to think about minus. So f of x plus g of x. Well, let's write it this way. We're not going to think about adding the outputs. Let's think of them as taking two power series, two formal power series, and adding them together. So f and g are the actual power series. We add them together formally, and what do we get? We actually get exactly what we would have got. Well, we get just what we think we should get. This will be equal to an plus bn times x minus x 0 to the n. This signifies adding them formally, as formal power series. When we add them, we just combine like terms. And the output that we get from these is just the sum of the outputs for the two things. So it works exactly like we would expect. And this also is valid within that radius of convergence. Multiplication also works. Fg of x. We will have, this time it's a little more difficult, right? Oh, you say this is the sum from 0 to infinity. Probably helpful. You knew what I meant. So this will be the sum. It's a little more complicated, so we're just going to call the resulting coefficients C's. At its center. And how do we get these C's? Well, the Cn, you get, well, let's just look at an example. A0 plus A1x plus A2x squared, and so on, times B0 plus B1x plus B2x squared, so on. We multiply these two things together. The 0th term, order 0 term, will be A0, B0. Here I'm assuming that it's centered at 2. Redo this with a different center. No problem there. Okay, now how do we get the x terms? We look at this right here will give us an x, and this right here will give us an x. So what we have is a0 b1 plus a1 b0 x. Then for the quadratic terms, we have a0 times b2 x squared, a1x b1x, and a2x squared b0. What does that look like? a0 b2 plus a1 b1 plus a2 b0 squared, right? And so the Cn is going to be equal to, in general, a0 bn plus a1 bn minus 1 plus a2 bn minus 2 plus dot 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 plus a n minus 1 b1 plus AN 0. We go in opposite directions, adding or multiplying together. That's a little more complicated rule than we had for addition and subtraction. But we at least have a rule, so we know what to do. It turns out that we can also do division. Oh, and what we get as the output here is, of course, f of x times g of x. So we get as an output the multiplication of the outputs, just like we would expect. We can also do division, but we have to be a little bit careful because we have to make sure that we're not dividing by 0. And this happens so long as g of our center is not equal to 0. As long as g of our center is not equal to 0, then we do division. And again, it's difficult to define exactly what the resulting coefficients will be. But they are there. They can be determined. And the easiest way to determine them is to multiply this thing out. So what we have is that if we multiply the g of x to the other side, then the f of x, which was from any 0 to infinity, a0, an x minus x0 n. If we multiply that g of x to the other side, we get some from this parenthesis n equals 0 to infinity, bn x minus x0 the n. So that's the g of x, and then multiplied by the quotient, which is there we're using p as the coefficient. So then we use that multiplication to work out relationships between all of the different coefficients, and then we can solve for them one after another. It's a little bit of work, and I won't go through it right now. In this case, in the multiplication, the radius of convergence stayed the same. In this one, the radius of convergence may decrease. So if we have that g of x is equal to 0 somewhere away from the center, then we can only go up to that point because we can't find the center. And let's see. Okay, we're at 11:20 right now, so maybe I'll just stop for today. So, do you have any questions? Oh, sorry, what?
I don't think so.
Okay. All right. See you tomorrow.